Good morning, everyone. My name is Rong Chen from Shanghai Jiaotong University. I'm glad to introduce our work about the graph processing on skewed graphs, which we jointly worked with Jiaxin, Yanzhe, and Haibo, Chen. Nowadays, we live in the era of big data. The value behind them attracts the data scientists to design a lot of the data analytic algorithms. Most of them can be abstracted as the computation on the graphs, such as that for the traffic, biological, and social networks. How to make the processing on big data efficiency has become an important and a timely topic. Most existing graph parallel systems follow think as a vertex philosophy. They will abstract the graph algorithms as vertex-centric programs to process vertex in parallel and communicate along edges. For example, the page rank can be expressed as the iterative computation on vertex. Each vertex will update its value, its rank, as a weighted sum of neighbors' rank. And the new rank will trigger the re-execution on the neighbors until all vertices reach the convergence. The vertex-centric program of the page rank should look like this, okay? Like this. The first step is to gather rank from the neighbors view in edges, and then update the vertex with the new rank. Finally, they will activate the neighbors to the via the alt edges. Recent research work revealed that graph processing in real world is challenging, since natural graphs usually follow the power law degree distribution and are commonly skewed. It means that most vertices have relatively fewer neighbors, while a few have many neighbors. Social network is a typical case of the skewed graph, such as the Xinlang Weibo, a Chinese microblogging, in which a top few stars has more than 70 million followers, while the normal user, like me, just have several hundred followers or even less. The vertex-centric program expressed the computation locally. So an intuitive way to implement the graph parallel system is to aggregate all resources locally before computation and to hidden the network latency, aiming to exploit the locality. While aggregate the followers of high-degree vertex like the star will result the million hundreds of followers will result in substantial imbalance and heavy network traffic due to aggregate these resources. And the high-degree vertex will be the center of the contention when receiving the messengers or be activated by the neighbors along all edges. So to remedy this problem, one solution is to split the workload of the one vertex to multiple machines, okay, for the load balance, and they are aimed at exploiting the parallelism. While the splitting comes at a cost, requires more computation, more communication, and synchronization. So for the low-degree vertex, it has just a few neighbors. The decomposition of it is not worthwhile. The irreconcilable difference between the low degree and the high degree of vertex makes a dilemma, resulting in a conflict design choice between the locality and the parallelism. Even worse, the skewed graph will aggravate the conflict, since the workload on both low degree and the high degree vertex are non-trivial. The former has the 100 million users, and the later has 100 million of the followers. None of them can be overlooked for optimal performance. However, the current system will using one-size-fits-all design and overlook the difference of the vertex. For example, the Pregel and the GraphLab focus on exploiting the locality. They use the edge cut to evenly assign the vertex along edges. Along with all edges, and aggregate all resources of a vertex on a local machine, maybe by using the messenger passing or replication. For skewed graph, the high-degree vertex will result in the imbalance, heavy network traffic, contention, as we have discussed. On the other hand, the PowerGraph and the GraphX are more focused on exploiting the parallelism. They use vertex-cut to evenly assign edges with replicated vertices and decompose the workload of a vertex into multiple machines for load balance. For skewed graph, most vertex has only few neighbors, so the decomposition of them will result in the suboptimal performance. Based on above analysis, we argue that skewed graph cost differentiates the processing on the low degree and the high degree vertex. We introduced the PowerLyra, differentiate graph computation and the partitioning on skewed graph. It will provide the hybrid strategy to explore locality for low degree vertex and the parallelism for the high degree vertex, as well as an optimization to improve the locality and reduce the interference in communication. We start from the graph partitioning. Our hybrid cut will differentiate the partitioning algorithm for low degree and high degree vertex, inspired by the edge cut and the vertex cut. Cannot use. The example graph we are used to explain the low cut and the high cut and how to integrate of them. We suppose the user-defined threshold is 3, then only vertex 1 in the sample graph is a high degree vertex. And the final result may look like this of our random hybrid cut. The red circles and the inverse ones represent the high degree master and the mirror, and the white circles and inverse ones represent the low degree master and mirror. We start from the low cut, which is inspired by the edge cut. It will evenly assign the low degree vertex to machines by hashing the vertex along with the edges in only one direction. Here, without loss the generality, we assume it's in edges. Okay. This design looks much simple, but it's also very effective, since it avoids duplicated edges and provided a unidirectional access locality, which can leveraged by our hybrid computation model. I will introduce it later. It also is efficient at ingress time, since it's only using the hashing. And it can provide load balance for both edge and vertex for the low degree vertex. At last, there's a bundle of ready-made heuristic of edge cut can be borrowed to further improve our low cut. We have implemented one called Jinger. The detail of Jinger can be found in our paper. For the high degree vertex, it is inspired by the vertex cut, but it only distributes in edges of the high degree vertex to machines by hashing the source vertex. It will also much simple. And also can provide load balance and efficiency and without duplicate edges. The most important feature of our high cut is that it avoids adding any mirrors for low degree vertex, since the edges will send to the master of the source vertex. The last question is how to efficiently construct the high degree cut. We use the general format edge list to illustrate our design, and assume the input graph files has been truncated and stored to the distributed file system like HDFS. The first step is that each machine will load a piece of the input graph file in parallel, and then all edges will be assigned using low cut by hashing the target vertex. And each machine will count the in degree of vertex to identify the high degree vertices. After that, all in edges of high degree vertices will be reassigned using high cut by hashing the source vertex. Finally, mirrors are created to construct a local graph as normal. We further introduce our hybrid computation model, which will decompose the workload of a high degree vertex for load balance and minimize communication cost for low degree vertex. In addition, our hybrid model also needs to similarly run all existing graph algorithms. For high degree vertex, we follow the gas model from PowerGraph to explore the parallelism. The computation on the single vertex was split into the three phases: gather, apply, and scatter. In each iteration, 4 messengers per mirror are used to distribute the gather and the scatter phase to multiple machines, 2 for gather and 2 for scatter. For low-degree vertex, we've reserved the gas interface and introduced a new model. It only provides unidirectional access locality with the help from our hybrid cut. It will ensure that all of in edges are linked to the master of low-degree vertex. This design is based on the observation that most algorithms of gather and scatter will veer in one direction. For example, the PageRank will gather data only along in edges and the scatter data only along the odd edges. Given the unidirectional access locality, then the gather phase can be executed in the local without any communication, and the 2 messengers can be skipped. Further, the messenger sent from the mirror to the master in the scatter phase is also not necessary, since the mirror will never be activated by the neighbors without the in edges. So consequently, for low-degree vertex, most algorithms, we only need 1 messenger per mirror. Our simplified model will minimize the communication cost, but it will limit the expressiveness to some algorithms that are requiring gather or the scatter in both directions. We name it the other algorithms. To seamlessly run these algorithms, PowerLyra will adaptively downgrade the model for the low-degree vertex by adaptively adding minimal messengers to handle this requirement or variety requirement of the other algorithms. The requirement can be detected at runtime transparently. For example, the connected component algorithm that has a gather none, but will scatter along all edges. It means the mirror may activated by the neighbors along its odd edges. So PowerLyra will add 1 additional messenger in the scatter phase to take back the activation messengers. We also provide an optimization to improve the locality and avoid interference in the communication. It's well known that graph parallel systems have poor locality. In here, we only consider this problem in the communication. Generally, the messenger exchange between the master and the mirrors are batched and sent periodically by the worker threads. And the messenger received from the different node will be updated to the vertex in parallel by the additional RPC threads. It will result in the poor locality due to the mismatch of the order, the sender and the receiver. And it will also result in heavy interference among all threads. Okay, PowerLyra to address this problem by extending hybrid cut at the ingress time to avoid the runtime overhead. We will using the initial state look like this. For most graph parallel systems, after partitioning, both master and the mirrors of all vertex are mixed and stored in a random order on each machine, depending on the order of receiving the edges of them. And I will use the 4th step to explain our design, even we implemented in the single phase. The first step is to divide the vertex space into 4 zooms for variety vertex. It will improve the locality of the sender and avoid the interference between the RPC thread and the worker threads. However, the problem within the zoom still exists. So we need to further to group the mirrors within the zoom according to the location of their masters. It will avoid the interference between the RPC threads. And we further to sort the master and the mirror according to the global vertex ID within a group. This will match the order of the sender and the receiver. Then it will improve the locality when updating the messenger to the vertex. the last question is, one messenger will be received from different machines. They will update it to the vertex simultaneously after synchronization. If the order of the mirror groups on each machine is the same, it means multiple mirrors may send the messenger to the same master and result in the contention. So PowerLyra will finally place the mirror groups on each machine in a rolling order to interleave the destination of master at the same time to avoid the contention. The optimization is a trade-off between the ingress time and the runtime performance. Since the execution, each operation executed on each machine independently, then the increase of the ingress time is modest, and we believe that a small increase of the ingress time is worthwhile for often large speed up in the runtime, especially for the algorithm with more iteration or evenly run multiple times. We have implemented the PowerLyra based on the latest PowerGraph. As a separate engine and the partitioning algorithms, it can support both sync and asynchronous execution, and it can seamlessly run all existing algorithms. Okay, to illustrate the benefit and the generality, we also implement the random hybrid cut to the GraphX. The evaluation, we will just evaluate the PowerLyra against the PowerGraph using various vertex-cut on two platforms using various algorithms and graphs. The overall performance of the PowerLyra is much good. Compare the speed up ranges from 2 to the 5.5 times compared to the grid vertex cut, which is the current default vertex cut of the PowerGraph. Since it can provide a relatively good balance between the ingress and the execution time compared to the original greedy heuristic vertex cut, like the oblivious or the coordinated, which mentioned in the original PowerGraph paper. You can find that, for example, the coordinated vertex cut can improve the runtime performance, but it will triple the ingress time for the Twitter follower graph. While our random hybrid cut can provide a comparable performance to the grid vertex, but significantly improve the execution time. To break down the performance, the improvements, we first compare the communication costs. PowerLyra can significantly improve reduce the network traffic by up to 75% and 50% compared to the grid and the coordinated vertex cut. There are two reasons. The first is most vertex is low degree. It means only one message is needed in each iteration for each mirror. And another reason is that our hybrid cut can reduce the number of mirrors. We also try to run the PowerGraph and the PowerLyra using the same hybrid cut we provided, and we find that our hybrid computation model can reduce about 30% execution time. Some audience may be interested in how the performance of PowerLyra compared to the other graph parallel systems for distributed or single machine platforms. First, we compare them using the general PageRank algorithms. PowerLyra can outperform distributed graph parallel systems due to fewer communication costs and improved locality. Since using the differentiate partitioning and communications. Further, our random hybrid cut can decrease about 25% of the execution time for the GraphX. For single machine systems, which will run one machine of our 6-node clusters, PowerLyra is efficient for the out-of-core graphs, despite the poor performance on single node. So we believe that PowerLyra can be further improved by using the novel technicals from the single machine systems. To shortly conclude our work, we argue that one-size-fits-all design may be resulting in suboptimal performance for the skewed graphs. And we introduced the PowerLyra. It will differentiate the computation and the partitioning on low degree and the high degree vertices. To embrace the locality and the parallelism. it will help our PowerLyra to outperform the PowerGraph and other systems for Ingress and Runtime. And our technical maybe can also benefit the other systems like the like the GraphX. Okay, that's all. Thanks for attention. I'd like to take the question.
Any questions?
Hi there, Derek Murray from Google. Can you go back to the slide where you compare against other systems?
Sorry.
Yeah,
go back.
the comparison with others. Thank you.
This one?
Yeah, that's great.
Sorry.
So you compared to a lot of graph processing systems specifically, but didn't compare to any general purpose data processing system. I know the next talk is going to talk about how you run PageRank on this graph using those systems. Did you look at the results for NIAD in SOSP 2013?
Yeah, we don't try the NIAD since it's more focused on the streaming processing and the data flows. It's more general. We don't try it.
Graph processing as well. It took about 1 second per iteration on 64 machines, 49 machines on that graph.
You mean the platform? Yeah. Why using the 6 node?
Okay, it took 5 seconds per iteration on 1 node.
Sorry.
It scaled smoothly between those. So what is the overhead in this system?
You mean, sorry, the overhead, your question is about what's the overhead from?
In PowerLyra, why is it so many multiples slower than a general purpose, not specific to graph processing system?
Sorry, I'm not casual problems. What about problems about the overhead from where?
Can you think of some reasons why it is so slow?
Sorry, which system is so slow? You mean the GraphX?
All of those ones.
All of those were so slow?
I'll only ask about yours, to be polite.
I think that the performance of the combo blacks is good. So slow, I think that the results also match to the other systems paper. The performance, they slow maybe some part apart from the programming language, since something is implemented using the Java, and our evaluated graph is skewed graphs. So I think the major problem is from the heavy communication costs. They will send more messengers, and for the giraffe, the problem is I think the cut will not much balance. And for the, I think the problem also has to the GPS. For the combo blast, the performance is good. It is using matrix-based computation, but the problem is from the ingress time is much longer. For the GraphX, I think the problem is from its memory allocation. It will using a larger memory footprint and cannot run Twitter follower, but the version we used is just a 1.1 version. So current version is 1.3. Maybe it has served these problems. Sorry, I'm not sure it's good.
Okay. Maybe we should talk offline about this.
Thank you. Sorry.
Okay. Any more questions? Let's thank the speaker. Thank you very much.
Thank you.